Okay, so welcome back to another video. So here today we are given a systems of equations, and it's given to us that if a squared times b plus a times b squared is equal to 1 and a cubed plus b cubed is equal to 2, we want to find the difference of a cubed and subtract with b cubed. So typically systems of equations, you would usually want to unsolve like the unknown variable / constant, but here this is a equation that we want to find the value of. So generally with techniques like this, you would have to deconstruct with the given equation. As you see from the first one, obviously you can actually factor out some variables from there or constants. Then you would have to be a little bit creative and do a little bit of different approaches to help build up other equations that will help manipulate things in order to get to whatever the goal that we want to achieve. So that's the premise is basically that technique that we're going to follow with that method. And generally, if you see a bunch of, or if you see like systems of equations of problems like in this format that it may look a little complex or complicated, then usually that's kind of the strategic move to follow in order to, enhance further thinking if trying to, establish and reach to the goal that you want to find. So basically that's today's video. It's going to be a short one. It's actually not that difficult for this one, and we'll actually just jump right in. So if we see for the first one, a squared times b plus ab squared equals 1. So let me first just write this again. What you'll notice is that you can actually factor out an a times b into that equation. And so what we have is the following. We would have a times b, and then we multiply this with a, and then add this with b. This is still equal to 1, okay? And if we want to construct more equations to help manipulate some things that, of course we want to achieve the following over here, then we would have to, get creative here. So suppose that let's actually multiply 3 to both sides of the first equation. So doing so, we have 3a squared times b, add this with 3ab squared. This is equal to 3. And I'm just going to keep the same thing for the second equation. So that'll be a cubed plus b cubed, and that's equal to 2. So let me actually label these as, equations 1, 2, 3. As the following over here. So now to further establish on what we want to do, let's actually add equations 2 and 3. So I shouldn't have put the red marker back. So let's see. Add equation 2 and 3. So we see that by adding these two equations together, we would get a cubed. Then add this with 3a squared b, add this with 3a times b squared, and then add this with b cubed, and then this is equal to 3 plus 2, so that's 5. You'll notice down the bottom, this is actually a formula for a difference of, or rather the perfect cube formula, and so that actually says that this is actually just going to be a plus b quantity cube, and then we have that this is still equal to 5. That's nice. So let's actually, now we can actually just take the cube root of both sides. So now we would have that a plus b is equal to the cube root of 5. So now moving further ahead, suppose that now we're going back to our equation 1. So we know that equation 1 is a times b is equal to, or a times b and then multiplied by a plus b quantity is equal to 1. Let's actually divide a plus b to both sides. So now we have a times b is equal to 1 divided by a plus b. Interestingly, we just solved what a plus b is equal to, that value. So we know that a times b is equal to 1 divided by the cube root of 5. So let's actually get a little bit more creative, and suppose if we start from here, let's actually square both sides of our equation. So now we have a plus b squared is equal to the square of this. So with exponents, you just move it inside of the radical expression inside. So this will just be the cube root of 25 square, or 5 square, which that's 25. So the cube root of 25 over here. Now, if I want, let's actually expand this a little further for the left-hand side. Let's FOIL this out. So we have a square, add this with 2ab, and then plus b squared. Of course, that's still equal to 25, or the cube root of 25, right? Let's actually do a little bit of more manipulation. So what I can do is, preserving this equality, I'm actually going to write it in this format. So we have a squared subtract 2ab plus b squared, and then add this with 4ab. This is still equal to the cube root of 25. You'll notice from the first three terms, this is actually can be rewritten from the difference of squares. So we would actually have, now this will be a subtract b square. And then add this with 4ab, this is still equal to, you know, the cube root of 25 over here. If we just subtract the 4ab to both sides, so a minus b squared equals 25 cubed minus 4b, we said that ab is equal to 1 over the cube root of 5, so we just multiplied this with the 4, so now this will be subtract 4 divided by the cube root of 5. Which hence, if we simplify this out further, you'll notice that we just get the common denominator, so you just multiply the cube root of 5 to both sides, share the same exponent, so you can actually move the 5 and the 25 and multiply those together. So it's a cube root of 25, and that's actually just equal to just 5. So there'll be 5 minus 4, and so this will just equal to 1 divided by the cube root of 5. And so far that's still a minus b squared, and if we take the square root of both sides, then we're also dealing with positive and negative values. So we have that a minus b is equal to positive and negative 1 divided by the cube, or rather the 6th root, since we're taking the square root, so it'll be the 6th root of 5. Going back to a cubed minus b cubed, now we actually have enough things that we want to, you know, everything we just build up in order to find the true value of this. So now a cubed minus b cubed, okay? So we know that from the difference of cubes, that's written as follows. This is a minus b, then multiply with a square, add this with ab, and then add this with b square. Okay, so we know what a minus b is equal to, so I'll just substitute that back in. So I'll be a positive negative 1 divided by the 6th root of 5. So we have a squared plus ab plus b squared. Okay, so what are we supposed to do from here? Well, you'll notice that we have an a squared minus 2ab plus b squared. So we said that that's equal to the cube root of 25, but we can also subtract a quantity of ab, which we said that it was 1 divided by the cube root of 5. So I'll just substitute that back in. So let's see, we have cube root of 25 in here. Then we subtract with 1 divided by the cube root of 5. And then just like before from earlier, we actually just, you know, find the common denominator. You'll notice it's just the same method. So in other words, if you do all this, the numerator is going to come down to 5 minus 1, and the denominator is still the third root of 5. And so we'll get that the inside is going to equal to just 4 divided by the cube root of 5. So now let's actually just put that back in. So plus or minus 1 divided by the 6th root of 5, and then multiply with 4 divided by the cube root of 5, okay? And if you just perform all this multiplication out, you'll see that this is actually going to afterwards in the denominator become a square root of 5, and then 4 on the bottom. And then if you want to, you can simplify this out even further, just multiply the square root of 5 to both sides. You don't want the square root or any sort of radical on the bottom. So therefore we have the final answer is just positive and negative 4 times the square root of 5, and then divided by 5. And just like that, we have solved our difference of cubes, a cubed subtract b cubed. And hence the video is done. Pretty much those techniques you can use for solving any sort of, you know, systems of equations, but instead of solving for, you know, a constant, you're really solving for the equation value itself. So usually typically methods like this is kind of the way to go. That's more of the, you know, the strategic move to perform all this necessary calculations. So yeah, that's pretty cool if you ask me.